Let's talk about physical versus chemical properties and physical versus chemical changes as well in samples. So when we say that a bit of matter undergoes a physical property change or a physical change, what we're saying is that something happened to the sample, and that change that happened, that property that was displayed, it happened without changing the composition of the material. So physical properties and physical changes, these things happen without changing the composition of the material. So for example, odor would be an example of a physical property. So if you have an orange sitting in front of you and you take a whiff of the orange, you can smell the orange smell. You didn't chemically change the orange in order to do that. That was a physical change because nothing chemically happened. No molecules got turned into something else in order to display the property of an odor. Color is the same way. If you look at the orange and you say, look at that, the orange is orange. There was no chemical change that had to occur in order to display that property. The color of an object can be measured. It is displayed without chemically changing anything. So anything that can be measured or is displayed without changing the chemical composition of the sample is a physical property. Melting and boiling points, by the way, are also physical properties that might seem a little bit backwards at first, because it might think, well, but things are changing. If you melt something, it's going into the liquid phase. It was a solid before. So, well, yes, the phase is changing, but nothing is chemically changing. You're not changing a chemical into some other chemical. It's still the same chemical, it's just in a different phase now. And for it to be a chemical change, you have to actually change the composition. You have to make a new molecule. And so that is what our definition of a chemical change or a chemical property is. This is something that is displayed by changing the composition. So flammability is an example of a chemical property. You can't measure how flammable something is without actually lighting it on fire. You can't just look at a bit of matter on the desk and be like, that is definitely very flammable. Like you can't just look at it and tell. You actually have to light it on fire and see how easily it lights on fire. So if it's very difficult to light on fire, if you have to put a whole bunch of heat into it and give it a whole bunch of oxygen in order for it to light on fire, then that is a very low flammability. Whereas if you just put a spark near it and it lights on fire, then it's very flammable. So to measure the flammability of something, you actually have to change it into something else, because when you burn something, it is chemically changing. It is not the same thing anymore. And if you've ever actually been to a bonfire or something like that, then you know this. You put wood into the fire, and as it burns, it doesn't stay as wood. It turns into ash and smoke, and some other things as well, but mainly ash and smoke is what that turns into. So a chemical property or a chemical change is displayed by actually changing the composition of something. So toxicity and corrosiveness are the same thing. If you take some acid and you measure how corrosive it is by putting in a piece of metal maybe into it to see how quickly the metal gets eaten away, that's a chemical reaction that's occurring. You're actually chemically changing both the metal and the acid are both changing in that. So that is a chemical property. So we have a few examples here. So dry ice, something you might be familiar with. You might not know what dry ice is, though. Dry ice is actually solid carbon dioxide. Carbon dioxide is kind of unique. It's not the only molecule that does this, but it's the most common molecule that actually does not go through the liquid phase at atmospheric pressure. So you will never, ever see liquid CO2 just in an open container. Now we can get liquid CO2. You just have to pressurize it. You have to just squash it, essentially. You have to put it under a really high pressure, and then you can get liquid CO2. But in just an open container, you will never have liquid CO2. At least not for very long. If you pressurize it and then release the pressure and open the container, it's going to evaporate very rapidly. But dry ice, when it's just sitting there on a tabletop, it undergoes what's called sublimation. It is doing a phase change from a solid to a gas. That is a physical change. That is a physical property that's being displayed because it's still CO2. You're not actually changing the molecule. You're just changing the phase. So before it was in a crystal structure, and then afterwards it is just a free molecule floating around in the gas phase. But you didn't actually change the molecule itself. So that is a physical change, a physical property. Sugar dissolving in water, same thing. This is a physical change that's taking place. Because when you take the sugar that was in a crystal and you pour it into the water, the sugar does not break apart into new molecules. It does break apart its crystal structure, so all the sugars aren't boxed in together anymore, but it's still just sugar. It's just now sugar with a whole bunch of waters around it instead of sugar with other sugar molecules around it. But you didn't actually change the molecule itself. So that is a physical change. If, on the other hand, you have a propane, it's not a furnace, but anyway, a burner here, stovetop essentially, a portable stovetop. That change that's happening here when you're burning the propane is a chemical change. Because again, burning anything is a chemical change. So you're actually taking those propane molecules, reacting them with oxygen in the air, and that makes CO2 and water. So that is a chemical change. Okay, so we have a few different things that are happening here. I'd like to encourage you now to pause the video, take a look at these different things that are happening, and just to specify here, we have candles that are burning, we have water that is boiling, we have a solution here that is starting to form this gray stuff on the side of the container. We have a match that is burning. We have meat that is browning, and we have a banana that is browning. So think about each of these things and decide if you think they are physical changes that are taking place or chemical changes that are taking place. So pause the video now. Alright, I hope you paused the video there. So the first one here, this is obviously a chemical change in that we have fire. So we have something that is burning. If you remember, I said anything that is burning, that is going to be a chemical change. But in fact, in this example here, we actually have some physical changes happening as well. Because if you've ever burned a candle before, you know that the wax down beneath the flame is melting. The heat from the flame is actually melting the wax, and that's what allows it to wick up the wick to be burned. So actually, in this case, we have both happening. We have both chemical and physical changes happening simultaneously. And that's perfectly fine. We can have both occurring simultaneously. If we have water boiling, like we have here, that is a physical change. Any phase changes going from gas to liquid, liquid to gas, gas to solid, any phase changes, that is going to be a physical change. With the match burning, that is a chemical change, because again, burning anything, that is a chemical change. Same thing here with part A. anytime you see a color change like this, something is going from blue to brown, there's a chemical change happening. Because if it was still the same molecule, in almost every case, and in reality there are some exceptions to this, they're very, very rare though, so we're going to, for our purposes anyway, pretend like those exceptions don't exist. With very rare exceptions, if there's a color change that's happening, it's a chemical change. Something does not turn into a different color while maintaining the same chemical structure in almost every case. And so you can probably guess that's going to be the same answer for these two as well. So for these bottom two, they're also changing color. So the meat, as you're browning it, that is a chemical change that is occurring. And I'm sure there's some physical changes occurring there as well. There's probably some molecules, maybe some fat or something that was more in the solid phase before, and as you heated it up, it simply just melted. But for the most part, that color change that's happening there is because of a chemical change that's occurring. There are actual proteins in the meat that as you heat them up, they change the way they're arranged, which would seem like that would only be a physical change, but they actually do form new bonds when they change their orientation. They form new bonds. That's what actually makes the meat tougher as you cook it more and more and more. It's forming more and more bonds until eventually it's just rubber and you can't eat it anymore. Well, not literally rubber, but it's as difficult to eat as rubber would be. So that's why you don't want to overcook meat. You want to limit the amount of those new bonds that are formed. And with the banana here, that is also a chemical change, and it's easiest to tell that because of the color change. And believe it or not, the chemical reaction that's turning the banana brown, in the broadest sense anyway, is actually the same reaction that is burning the match. It is actually a redox reaction. So essentially that banana is just very, very slowly burning. It's burning without a flame, but that's okay. You actually don't have to have a flame for redox reactions to occur. Obviously they're much, much faster if there's actually fire, but redox reactions don't need flames to occur. So this is redox reaction, and this is also a redox reaction. So the banana is sitting there burning. That's what's causing it to turn that black color. Alright, do one more here and then we'll call it for this video. So determine whether each change is physical or chemical. What kind of property is being demonstrated in each case? So again, go ahead and pause the video, take a look at these four, see if you can come up with an answer. Alright, I hope you paused the video there and tried to work this out for yourself. So part A, evaporation of rubbing alcohol. That is a physical property. So this would be demonstrating the physical property of the boiling point, I guess. So part B, the burning of lamp oil. That is a chemical change. It's displaying flammability. Part C, bleaching of hair with hydrogen peroxide. That is a chemical change. And I guess you could say that is displaying the chemical property of I'm tempted to say toxicity because hydrogen peroxide is actually quite toxic, but it's not actually acting as a toxin to your hair. It's more not sure what the actual chemical property would be described there, but it's bleaching your hair. It's and by the way, don't just go use hydrogen peroxide for everything. I've seen posts on Facebook and things where people are like, here's 100 different things you didn't know you could do with hydrogen peroxide. I would highly encourage you to do 100 different things with hydrogen peroxide. The hydrogen peroxide you get from the store is pretty low strength. I think the strongest you can get it is 3%. But even so, hydrogen peroxide is really nasty stuff. When you put hydrogen peroxide on your wound, which is when it's one of the more common uses for it is as an antiseptic. So you get a cut and you put hydrogen peroxide on it, and you see it bubbles and it hurts. What it's doing there is it's killing everything. It's killing the germs, it's killing your cells, it kills everything that I can get in contact with like that. Now, thankfully, you're really big and you have lots of cells, and you can handle losing a few cells to hydrogen peroxide there. You'd rather lose a few blood cells and things like that than have germs get into your wound. But I've heard of people like using hydrogen peroxide as a mouthwash every night. Like that is not good for you. That is really not good for you. Hydrogen peroxide is very, very chemically active, and I would never suggest coming into regular contact with hydrogen peroxide, even in its relatively low concentration like you get at the store. Part D, the forming of frost on a cold night. That is a physical change, a physical property that is being displayed there. That would be sublimation. Deposition. Sublimation is the opposite direction. So that would be deposition, because you have water that is in the gas phase, and it goes directly to the solid phase when it forms frost on your vehicle, which is super annoying, because then you have to scrape it off the next morning. So that will be it for this video. In the next one, we are going to talk about the importance of units, which is going to be a really, really big topic and a very important topic. So I look forward to seeing you in the next video.